Thank you, Alan. I appreciate that. And thanks to all of you for joining us today. It gives us an opportunity to share some of the fine work we're doing on the AIRS project, as well as show you some directions we're moving at JPL to try to transition this technology into more affordable sensors and to do things a little bit differently and get some new perspectives on the Earth's atmosphere. So I first would like to acknowledge that there's a lot of participants who made this talk. It's a 50-minute talk, and I have a lot of slides. We have the AIRS project team at JPL who's done a wonderful job of calibrating, operating, and producing data products for the scientific community, as well as getting these products in the hands of NOAA so they can use them to improve forecast. The AIRS science team, from which a lot of the material I will show was generated, our partners at the Goddard DAC who distribute our data and make it available to the public. And you can get all this data yourself, free, anywhere. Anyone in the world can access this data. I think that is one of the gifts that NASA has provided to the community. And then, of course, the CubeSat team I'm working on, which is called CIRAS. I'll tell you about that in a minute. A lot of great engineers helping to actually make this a reality. And our contractors, there are a lot of contractors who are involved in the AIRS development and in the CubeSat I'm working on now, but I do want to acknowledge a few of them, including BAE Systems, who built the AIRS instrument. Fabulous job on that. Ball Aerospace, who's building the optics for my CubeSat. IR Cameras, who's doing the doer. And Blue Canyon Technologies, who is our spacecraft provider for this CubeSat. Also, I want to acknowledge our sponsors, NASA Science Mission Directorate. They provide us funding for the AIRS, and in 15 years, I think that shows their dedication to this mission. We've been in the extended mission for almost 10 years now. And the NASA Earth Science Technology Office, who actually funds these CubeSats, and I welcome you all to keep an eye on the ESTO project, ESTO homepage for new opportunities for all of you to do something similar to this in the future. And then the NOAA, NESDIS Office of Projects Planning and Analysis, who are greatly interested in our CubeSat effort here and supporting a study that's helping us understand what we need to do for the future as well. Okay, let's see if I can get this to work. So, you know, remote sensing of the atmosphere and the Earth's upwelling radiance goes way back. And you know, the days of Vern Suomi and the folks at Wisconsin, where Alan is from, they've been a big part of this whole, they've been pioneers in this whole effort. So this was one of our first satellites, just happened to be launched in about the time of I was born, so it goes way back. But some of these pioneers really made the point that the upwelling radiation can be used to understand Earth's energy balance, which is related to climate. Following that, there was a long series of Tyro spacecraft that really were the workhorses of taking this video imagery. RCA Corporation, you remember your RCA TVs? A long series of satellites, and NOAA has been very good in a lot of these were developed by NASA originally, but NOAA has been good in picking these up and using them operationally. And then more into the 80s, and we have the long line. We start getting into some of the infrared sounding instruments, like the HERS was one of the high-resolution infrared sounder, had multiple spectral bands in it so that you can sound temperature in the atmosphere and see water vapor. And then there were some interferometers back then and limb sounders. So this science really started to take root in the 70s and 80s. And that brings us to today, where, you know, NASA has a large fleet of satellites. I'm not showing the NOAA series here, but I do want to focus on two particular satellites that are up there, that the Aqua spacecraft, which houses the AIRS instrument and the MODIS instruments, and the Suomi NPP spacecraft, which was originally, it's a NASA-NOAA partnership there to demonstrate the pathfinder for the Joint Polar Satellite System. So I'll talk about these mostly, and then I'll get into the CubeSat at the end. So this is what one of these satellites looks like. This is the Suomi NPP. It's the precursor to the operational Joint Polar Satellite System. And this system is really the state-of-the-art of what we have today in terms of full service satellites to provide operational data, operationally for weather forecast prediction. We have the big workhorses on here, like the ATMS, the microwave sounder, provides all weather temperature and water vapor profiles. We have the CIRAS on here, which is the current generation of interferometer thermal sounders, provides temperature and water vapor profiling with higher vertical resolution than the microwave, but it's more sensitive to clouds. So these two instruments, the microwave and the infrared, work together to provide the best all-weather temperature and water vapor profiles. We have the imager, VIRS. All of these, if we go back to looking at some of those earlier sensors, it was just imagery. Imagery is real important for understanding cloud distributions and understanding weather patterns and also surface phenomenology. The ozone mapper, which provides it's the latest addition for monitoring ozone in the atmosphere, in particular the ozone hole, and CIRAS, which is the radiation budget instrument that provides energy balance, very useful for validating climate models. And so, whoops, wrong direction. Here, let me try this again. So the Aqua spacecraft, which really was the predecessor to the SWOMI NPP spacecraft, I'm kind of going back and forth here a little bit, but I wanted to point out here that here's the AIRS instrument. It is the one I'll tell you about and show you a lot of data, the infrared sounding instrument and how it works. We have the MODIS instrument here, which is up in the front here, and this satellite was built. It was launched there was one launched in 1999 and another in 2002. So this is 1990s technology. As Alan said, I spent most of my career since 1985 working on MODIS, and then came to JPL and started working on AIRS. So I have almost 30 years on this platform in my career, and I'm very pleased to say it's still working. So, okay, I'm sorry. And then we still have the CIRAS on here. We have two CIRAS instruments, and then our microwave instruments, as well as a conical microwave instrument. This microwave instrument provides higher spatial resolution microwave measurements, very good for surface temperature, ocean temperature, and sea ice detection. I've got to get this figured out. Apologies. Here we go. So after AIRS was launched on Aqua, a lot of folks decided that they wanted to join us in the same orbit. And the reason is having concurrent temperature and water vapor data and imagery is pretty helpful to other measurements like, carbon dioxide and CloudSat for cloud properties and aerosols. And a lot of these other instruments really appreciated the fact that we could join them. And we appreciated them being in the same orbit. We do a lot of intercomparisons with these data sets. So this is our first constellation, if you will, at NASA. But the point I want to make here is that these instruments on the Aqua spacecraft are designed to provide global daily coverage. And the way they do that is by having a scanner on board that scans cross-track, if you will. Here's the flight direction in this figure. And so they scan a cross-track to that and with a scanner. And that allows you to achieve basically cover the whole Earth for the most part. I mean, there are some gaps in here on the AIRS, and there are no gaps on MODIS and CIRAS, but the intent is to provide global daily coverage. And this is an animation showing how these instruments operate, and you can see as it's going along, the various instruments, this is CIRAS showing now here, but each of the instruments has a scanner on board to scan it cross-track. You can see the passive radiators here for the AIRS, and here's the MODIS. This is for, MODIS has a focal plane that is passively radiated, passively cooled, and the AIRS uses passive radiation for its optics. And this is the conical microwave AMSR-E instrument. It's a very large antenna, and the whole thing moves. It is no longer operational. And you can see how these things provide a wide swath. Okay, let's continue here. Some of the technologies that AIRS pioneered were the active pulse tube coolers. This is a dual redundant cooler. Again, this is still operating 15 years after launch, and with no anomalies at this point. Evacuated dewar with a cold window, very sophisticated dewar that allows the focal plane to be in a dewar and not be subject to icing while it's in orbit.
The focal plane itself was made up of linear arrays of mercury cadmium telluride, and this program actually pushed the cutoff wavelength of mercury cadmium telluride at the time to 13.7 microns, and that was a pretty big deal at the time. So some of our detectors are a little bit noisy and have funny noise properties because they were some of the first mercad telluride to be developed with this kind of a cutoff wavelength, and this was in linear arrays. And then it had a complicated optical system that images the pupil onto the focal plane, and each focal plane has its own set of afocal relays. So it's a pretty complicated effort to be able to do this with these linear arrays. The area arrays we have now make things a lot easier, so I have an advantage when I do the CubeSat. So what this sensor does is measure the upwelling radiance of the atmosphere in the infrared. And I apologize, this is in wave number at the bottom, but if you invert your brain a little bit, it goes from about 3.6 or 7 microns all the way out to 15.4 microns. And it's hyperspectral, so AIRS has 2,378 channels that measure this spectrum. And the way we measure temperature is a temperature profile is by using these CO2 absorption branches. By sounding down, each channel really measures, has a different amount of absorption. So what it's effectively doing is measuring the temperature at different altitudes in the atmosphere. This is brightness temperature, so when it's up here, these channels see the surface, and these ones are looking up in the stratosphere. We also have a temperature and sounding branch down here, and these are water lines right here. So keep that in mind, and I'll tell you a bit more about it later. So what we can do with this, since AIRS maps the entire planet every day, we can make effectively a video with the frame rate of 1 day of the atmosphere in 3 dimensions. And here's a slice of that, an example of that during the polar vortex problem we had in 2013, where the East Coast was getting hammered by storm after storm after storm, and it's interesting because we could actually see when the polar vortex would dip down and produce this kind of cold spell that would go very deep into the southern states, and they bring all sorts of terrible weather with it. But it's not just the temperature that we see. We also see water vapor, and we use this for studying transport. Carbon, this is methane. We see methane in the upper tropospheres. So we can see it, transport. We do not see methane near the surface. We see carbon dioxide. We have some of the first global maps of carbon dioxide. I'll show you some of that. Temperature again, cloud properties, carbon monoxide. We see giant plumes of carbon monoxide being lofted into the atmosphere from biomass burning every year. And then the ozone hole, which we have a great animation coming up on that as well. These are isosurfaces. I'm introducing that here so you can get an idea of the fact that we do have a 3-dimensional data set. You can see here over the desert we have a hot surface here, and then you reach the tropopause here where things get cold, and then they start to warm up again. So this is just a really interesting figure. But we do the same thing in water vapor as well. We're coming off the coast of California during the winter, and we hit the warmer ocean. This is probably a night granule, and then we see the water vapor rise, lofted a little bit as we get more of it in the atmosphere. Oh, try this again. So with this 3-dimensional daily data set, we're able to actually make animations of isosurfaces. What you're looking at here is the formation of the ozone hole. So with the ozone hole, ozone is depleted, so in order to find the isosurface, the isosurface has to go higher in the atmosphere in order to find the same concentration of ozone. So what you're seeing here is the ozone hole, and you can kind of see some of these wisps of ozone moving around. You're seeing the formation of the ozone hole in the polar winter. And what happens is this is done every 12 hours because we're in the near the poles, we get more overlap of the orbits, and we can do this every 12 hours. So we're trying to improve our timeliness of the data. Now we have three of these sounders in orbit. We have the AIRS, the CIRAS, and the IASI, and we're still working on trying to merge these data sets for to improve timeliness of all of our products. So some of the science applications and operational use of the data, this is a good example of improvement in hurricane tracks, where this particular investigator tried no AIRS data and then with AIRS data and was able to show that for this terrible tropical cyclone that hit Burma, we were able to improve like 5 of the 7 forecasts the days prior, and if this data were in the system, we could have done a better job predicting it. Of course, this is all done after the fact. But in general, and this is pretty much typical, the infrared sounders, here I'm showing IASI and AIRS, but CIRAS is comparable, have among the highest impact of all the different data sets assimilated into the operational forecast systems. The microwave have the highest, and that's a big part of that is the fact that there are more of them and that they see through the clouds. But this is doing a pretty good job here for the infrared. There are a lot of users all over the world who access this data. Shown here is, in fact, most of the data that for Aqua is from foreign countries. So we're happy to participate in an international science program. For AIRS in particular, we're doing pretty good here in blue. MODIS is the big workhorse in the scientific investigations, but AIRS releases a number of dozens of publications every year, peer-reviewed publications. So, and this is basically really shows the value of this program to NASA and the scientific community. So, looking at a few of these papers, Abhay Devastali did a very nice study trying to understand what's happening in the polar regions. In particular, with the melting in 2007, there was a really bad polar melting. And I think it's kind of coming back again in the 2015s, but this is an old study. But what he found was that the frequency, the actual amplitude or strength of the temperature inversion in 2007 was particularly larger than many of the prior years. So we're seeing the effect of atmospheric circulation bringing warm air into the polar regions and causing temperature inversions that effectively contribute to the loss of ice. Very good study. He's continuing these studies. And other things we do is validate climate models. I think we all are aware that climate projections for future warming have a high degree of uncertainty. So we're trying to reduce these uncertainties and improve predictions for societal benefit. And what AIRS has done is we're trying to understand feedback mechanisms. These are a number of feedback mechanisms, water vapor, clouds, aerosols. And what ends up happening here is, what this means is that if carbon dioxide is going to raise the temperature in the atmosphere by 1 degree, that you will actually experience a 2-degree warming because of the impact of water vapor. So water vapor turns out to be a primary greenhouse gas. It's not the dominant greenhouse gas in our atmosphere. And so what AIRS has done is validate the strength of the water vapor feedback so that we could verify that the models were correct. And the way we did that, actually the way it was done by, oops, let's go back here. Okay, here we go. I'll play this movie so you can see our isosurface of water vapor while I'm talking. In this investigation, Andy Dessler at Texas A&M looked at a warm year and a cooler year and compared the vertical distribution of water vapor as a function of zone, this is latitude here, and found that in the warmer years, water vapor tends to build up. There's more water vapor in the upper troposphere. And what that does is it acts as a blanket that tends to isolate and contribute to more warming. And that's how we confirmed the water vapor feedback strength. The other things we're doing is understanding where the water vapor goes. Some of the models are showing that the models are actually a little wetter in the upper troposphere at the southern extratropics, and really wetter down here. So these kinds of things, we see there are little biases in the model that may compensate the total upwelling radiance that instruments like CIRAS would see. So the AIRS is providing a new dimension, a vertical dimension of the spectrum. All right, so let me see here. I'm going to get this right one of these days. Another very interesting capability of the AIRS is because we're using CO2 to measure temperature, we're actually measuring CO2 as well. Dr. Mush Shaheen was able to develop an algorithm for retrieving mid-tropospheric carbon dioxide. And what you're seeing here is a detrended seasonal variability of carbon dioxide. In other words, we've taken out the 2 ppm per year that it's been growing just to see how things behave seasonally. And the very interesting feature here is that as you see, as things green up, you could see less carbon dioxide. And then as things get cold and there's no plants to absorb the carbon dioxide builds up again. And I think this is the first real animation of the breathing of the Earth's atmosphere. Oh, darn, I got to go up. All right, here we go. Other things we can do, we have climatologies of temperature and water vapor, and we can look for anomalies. This is a Somalian drought that showed an anomalously dry year here, and then temperatures, we had like a heat wave, we can see this kind of thing. We measure carbon monoxide. As Alan was saying, we have trace gases. We can see biomass burning in the tropics here, in the Amazon and the Congo. And these plumes are gigantic. They travel, across the oceans, and fortunately, they don't they're not hazardous in themselves, but they do contribute to ozone and other pollutants. Here's a good example. We had the station fire in California in 2009, and we actually saw that plumes reach Houston and found that there was a correlation between poor air quality in Houston and the location of these plumes. In this figure, we're showing sulfur dioxide, which is indicative, it's from a volcano. And we see these, and we have a real-time alert system now that allows us to detect these and provide that information to NOAA and other government agencies to alert them for the aviation industry. And they need to know where there's ash in the atmosphere. And the sulfur dioxide is a good proxy for the ash. Ozone, we do measure ozone, and we're able to see somewhat of a vertical profile of the ozone, so we can see sometimes what happens is ozone tends to build up and and there's mixing between the troposphere and the stratosphere, and they call it stratospheric tropospheric exchange. And sometimes these ozone plumes can bring down a large amount of ozone into the lower troposphere, and that confuses some of the regulators because they're not certain if the increase in ozone is due to the factory producing more ozone or if it's a natural weather event. And so what we're trying to do is provide information that can help differentiate between naturally produced ozone and that produced by industrialization. Another very interesting study is drought, how to use AIRS data to predict drought. Since we're measuring relative humidity, we found that relative humidity is actually a better indicator of an upcoming drought than precipitation. And some of our colleagues at University of Irvine, UC Irvine, were able to show that you can get about a 2-month lead time in onset of drought by looking at humidity. So we're working with drought organizations around the country and to try to provide AIRS data support drought prediction. AIRS is going strong. We have another 5 years of data of life left in our spacecraft in terms of fuel. Everything else seems to be working very well. So we have, this is really a time that we're spending now to cross-calibrate our AIRS instrument with the CRIS instrument and the EASI instrument so that we can continue this type of data products for the scientific community. So I want to tell you a little bit about the CubeSat we're developing at JPL and give you some of the basis of that. So the National Academies of Sciences, I'd like to start here because they were tasked to look at the value of CubeSats for applications of science investigations. And
what they concluded was that there's a great opportunity here for scientific measurements to be made in these CubeSats. I think the enthusiasm, at least I found, was greater than what I expected, that they really think that there's value for weather and climate and space weather. And in fact, there is a wide variety of satellites being developed now. I think CubeSats are exciting because they bring the possibility of remote sensing down to university levels, to corporate levels, rather than it just being a government-only club. So this is an opportunity for all of us to get our measurements in space and improve our understanding of our Earth in many ways. So the way these work is that you have a primary launch vehicle, a primary payload that's contained within the main body of the launch vehicle, and then they attach these launchers onto a portion of the spacecraft, and they basically, when they get up there, they're spring-loaded, and they open up the door and they pop them out. At this time, most of these don't have propulsion. I think people are still working on propulsion for these, so they drift around, and after a couple of years, they degrade and burn up in the atmosphere. A number of companies are out there who are developing CubeSat buses commercially. I'm showing Blue Canyon here, but again, there are many others that do this work. What we are going to be using for our CubeSat is this 6U bus here. The panel's configuration is a little different. Here's some examples of some of the 6U bus structures. I took some photos when I was at the SmallSat conference last year in Logan, Utah. By the way, the SmallSat conference is happening right now in Logan, Utah as well. And every year we do have a CubeSat conference here at SPIE. This year we skipped it because it was at same time as the one in Logan, but I encourage you next year to join us at CubeSats and Nanosats for Remote Sensing Conference here at SPIE in the remote sensing track. And so what we're going to be doing on our CubeSat is mounting all of our instrumentation to a plate that fits on the top of this. It's actually, the plate is not shown, it's removed so you can see the inside, but this is where our payload goes. And our spacecraft actually takes up 2 of the 1U compartments. In CubeSats, a U, for those of you who aren't aware, 1U is a 10 centimeter by 10 centimeter cube. And so what you're seeing here is this, in this configuration, the satellite is taking, this avionics is taking up 1U, leaving 5U for the payload. In most cases, it's more like 2U for the satellite and 4U for the payload. Now, JPL's picked up on this idea of CubeSats. We started with Griffix, and we have a number of other ones that are going to the moon, and we're looking at radiation effects and communications, and here's one that is a microwave sounder. So we're picking up on this idea and running with it, and we think that it gets to be pretty exciting when you can do this. However, we have to change our thinking. We're used to building big satellites, and big satellites have a lot of money to be able to do a lot of the things, to do it right, and to get a 15-year mission like we have on CIRAS. Well, these CubeSats, we don't have a lot of money in the first place, and we have to find that good balance between reliability and affordability. So looking back now at the particular CIRAS instrument and the technologies developed, I think I showed you some of these, the optics, detectors, and doers. There's been a huge evolution in industry that has really helped enable what we're trying to do. I was really surprised when I found out that we could do infrared sounding in a CubeSat. But folks showed up with these great technologies like these miniature coolers. This is a Rycor cooler, but there are other micropulse tube coolers by Northrop Grumman and Lockheed Martin that are actually longer life and better performance than some of these. And the CIRAS uses our CubeSat as an evacuated doer. We don't have as sophisticated a doer as the CIRAS did, but we found one that will suit our needs. And we have some new detector material called Hot Bird. It's a barrier infrared detector. I'll show you a little bit about that.
And then our new grating spectrometers take advantage of these two-dimensional focal planes, and we have a wide field all refractive optics here. So let's see what some of this looks like. So basically we decided to take this technology and propose it to NASA's Earth Science Technology Office in-flight validation of Earth Science Technologies program. And the idea being that we propose to demonstrate in space key technologies for infrared subsystems, including hotbird detectors, an emerging grating spectrometer, and a black silicon blackbody. I'll show you some of these in a minute. Demonstrate that we can do temperature and water vapor soundings, and advance the TRL of the technologies themselves. JPL will be developing these key technologies, the hotbird, emerging grating, and black silicon, and Ball will be actually developing our optical system in which the emerging grating will reside. IR Cameras is building the Doer, and Blue Canyon our spacecraft. It's a 6U spacecraft. We're going to be in a low Earth orbit. We have funding for 3 months, but hopefully we can get more money if the mission is successful at that point. And as I mentioned, it's funded by ESTO with studies. NOAA is watching and helping us with their study of the next generation Earth observing nanosatellite. That would be sort of an operational version of one of these I'll tell you a little bit more about. And we're scheduled for launch in the 2019 timeframe and have been selected by the CubeSat Launch Initiative. So remember this spectrum I was showing you. What CIRAS does is take advantage of the fact that we also have a temperature sounding branch out here in the shorter wavelengths. We did not want to do the long wave right off the bat. It's a much more difficult problem. We don't have all the technologies available right now. So we decided to look at the midwave and see what we can achieve here. The complication being that there's still some reflected sunlight here that can get into our data set. And so this is going to be an experiment for us to learn how to deal with that. However, we have a good temperature sounding branch here. It doesn't go as far into the stratosphere as the long wave, but it seems to be very good for lower tropospheric measurements, certainly to mid-troposphere. And then you can see this is where air stops and it picks up this side of the water band. These water lines go all the way down to here in the 2200 wave number range. And so we're picking up some water bands here. I'll show you what that looks like. So if you take that spectrum and look at what the spectrum for CIRAS is in this orange curve here, you can see here's our temperature sounding branch. And instead of plotting temperature, I'm plotting radiance here. And you can see here's our temperature sounding branch, and then we get into the water lines. Also overlaid on this plot is the spectral resolution of CIRAS in purple here in terms of wave numbers. We're about 1.2 to 2.0 wave numbers in spectral resolution, and showing the AIRS instrument spectral resolution here, which is comparable to what we're seeing for the temperature sounding branches. And of course, they didn't go into the water line on this side. But we do have good spectral resolution to resolve these water lines. And our analysis shows that we have comparable sensitivity in the lower troposphere to the CIRAS instrument. When we get in the upper troposphere, we're a little bit degraded. So the way CIRAS works, it's taking advantage of a large two-dimensional focal plane of hotbird detectors. And what we do is we take a slit we image the slit from the spectrometer, which is a very wide field of view. This is a 16-degree field of view. We image that onto the ground and have their scan mirror scan it. We have a unidirectional scanner that I'll show you a little bit more about in a minute that scans the field of view, and the image actually rotates. That's why you're seeing these lines at the end. And in order to make a pixel, as it scans, we average, in this case, shown 3 frames of data at 11.8 hertz, and we average 42 pixels along the slit to get the spatial dimension. So we're able to build up a pixel of 13.5 kilometers, which is our requirement. Now, we also can change our frame rate, scan rate and our pixel binning scheme and achieve a higher density, higher resolution. We can actually get to about 3 kilometers over a 150 kilometer swath. And we believe, and studies have shown, here shown by Joel Susskind, that we can have higher yield if we go to 3 kilometers in severe storm areas. So this will be a very interesting experiment. We may be the first sounder
that has spatial resolution at 3 kilometers. And that will be real exciting to see how that improves the yield. So here's a demo, not a demo, this is really a prototype of our scanners, our scan motor, and we're demonstrating the scan pattern. It's a stepper motor, and in this first iteration you can see it kind of a little bit jittery, and we have new code that cleans that up. But basically that's how it scans. It's a very slow, almost 20-second Earth scan. It pops up to the space view, the black body, takes a look at that for a couple frames, over here to the space view for a couple frames, and then it starts the Earth scan again. It's a very unusual scan pattern. Just show it, watch it, flip it around one more time. There you go. So as I mentioned, we have the normal global mode scanning pattern. We have a zoom pattern, but we can also rotate the spacecraft. We own the spacecraft, and there's nobody else on board. That's one of the advantages of a CubeSat. So we can do things like this, experiments, to see how a push broom would look. Of course, we don't like to fly too much with the large area and the ram direction because it slows the spacecraft down. There's a little bit of atomic oxygen, but for a few minutes, it's not a big deal. And we can acquire data in a push broom mode, and even a higher resolution mode. If we start to average things spectrally, we can get to 1 kilometer and test some imagery. These experiments would be interesting. We can look forward and look backward and take 2 measurements of the same area and potentially see atmospheric motion vector winds. We hope to do that. So inside this system, and I'll show you a picture in a minute, we have the scan mirror assembly, which consists of the motor and the mirror and an indexer that tells us our scan position. We have a black body in there, motor controllers. Here's our optics assemblies, our doer assembly. We have 2 coolers, one to cool the optics, one to cool the focal plane. Set of electronics for controlling the payload and housekeeping, and to read out the electronics. These boards, the proximity electronics and the detector readout electronics, are commercial boards. So we have a real challenge now with electronic parts that are susceptible to single event latch up, and we're working on that right now. This is our early CAD of our system. We're not quite done with the front end here, but basically you can see the spectrometer in here that Ball is developing, supported by G10 bipod, G10 bipods that thermally isolate the spectrometer from the chassis. The spectrometer has to operate at 190 Kelvin. The doer itself over here in this system consists of the cooler and an evacuated cell here, a cell that keeps the focal plane at 115 Kelvin without any without icing. Attached to the doer is the proximity electronics and camera electronics. Proximity electronics right here around the rim, and the camera electronics are right here. So this whole assembly is being delivered by IR cameras, and they're doing a good job. And then inside there is the hopper detectors. We're using electronics that we're borrowing from another CubeSat mission called Tempest-D. This is the processor unit, and here you can see emerging grating. And we have a black silicon black body, not shown here. We haven't really quite finished the front end of this in this early drawing. So we've successfully developed our detectors. On the first lot, the hopper detectors produced 12 usable arrays for our project, all met specifications. It's just a testimony to this new technology that uses different materials for making the detectors. Materials from periodic table that are in 3 and 5, columns 3 and 5 rather than 2 and 6. So it's a new kind of material. You're seeing an animation here of the physicist who actually designed the material, and he just ran up the stairs and was kind of flushed, which I thought was interesting. You could see the veins in his hands, but it does show the dynamic range of this focal plane. It's very high and very low 1/f noise. That's why we can get away with the low scan rate. The spectrometer itself is being developed by Ball. They're doing a great job. They know how to hold these lenses with flexures, and the whole system is isothermal, which means that to first order we can align it in ambient, and they can align it at ambient, and we can, when we're doing our system tests, we can use it at ambient, and it maintains its focus when it achieves operational temperature of 190 Kelvin. So I'm anxious to see how well that works. And then there's our black silicon. We built a lot of this for slits, and they're flying now on several instruments. But we're going to try to use it as a black body, have a bigger piece of it. And it's very, very high emissivity, very low reflectance over a very broad spectral range. It's kind of like carbon nanotubes, but perhaps a little bit more robust. The satellite is being built by Blue Canyon Technologies. They have developed this solar panel arrangement for the Tempest D project. And basically what we do is collapse this solar panels down to a stowed position and slide it in the canister. And the canister has these bumpers that keep everything closed. And as it pops up, it deploys. As it pops out, I'm sorry, it deploys. And it has this funny canted configuration in order to optimize the sun angles over the course of the orbit. Oops, okay, here we go. We've looked at the power that we're going to require. This is really a challenge in CubeSats, getting the power you need. You can see how many panels we had on there. We're consuming about 25 watts of power. Fortunately, when we're cooling, we use the most power, but fortunately, when we're done cooling and we reached operational temperature, our power levels go down, so then we can start to turn on things like the camera board and collect data. They've done an analysis of our power profile and found out that for our system that we can turn the camera on, we can turn the coolers on, achieve operational temperature, and leave it there for the duration of the mission. And the spacecraft, what it can do in order to achieve enough power on the batteries, can provide us one full orbit of data acquisition. But then it needs to maneuver so that the panels are optimized to charge for 2 orbits. So we have 2 orbits of power in the power saving mode and power production mode, and then we have a 1 orbit of data collect. Now that's perfectly suitable for our mission because we're a tech demo and we're not trying to collect everything everywhere all the time. But we know how to go to 100% operational mission by changing some of the, using more passive radiator approaches and changing our thermal approach. So basically, what are we planning on doing with this technology? There are several opportunities that we can look at. One is in particular, and this is why NOAA has been a part of our team, they're looking at it as a possible way to mitigate a loss, a gap, if you will, in coverage of these operational infrared sounders. You gotta realize some of those first satellites that we're showing are billion-dollar satellites, and that's very difficult to have a hot spare sitting around if you've had an unfortunate accident, to have one ready to go. I mean, that's a billion-dollar insurance policy. These things are small and quick. You can get them up there quickly and cheap, and they may not do 100% of the job, but maybe they'll do 50 to 80% of the job, depending on how far along we are in this. And so that's what we're trying to find out, is that can we be a robust backup system? And there's a parallel effort to this EON infrared effort. There's an EON microwave effort. In fact, they're ahead of us, and this is Bill Blackwell at MIT Lincoln Labs is developing technologies that can be used for a microwave version of this. The other thing is improved timeliness. I was trying to emphasize earlier that the wide swath of these infrared sounders and imagers provides global daily revisit. Well, that's great, but we really want to do better than that. And the geostationary instruments, and I know there'll be some geostationary sounders in the future, can provide hourly revisit of sounding information, which is going to be extremely valuable. Well, these CubeSats complement that by doing, if you have several of them in orbit, you can add times to your orbit. For example, if Ayers and Iazi are here, Ayers and Chris are about in the same orbit. If we add one more satellite, we can add CIRAS might, for example, the first one might have an orbit here, and each time you add a satellite, you can start to build up additional times during the day in acquisition.
And you can see with 3 or 4 satellites, you're in this situation where every couple hours you're getting global coverage, and that really may be a good place to be in the future. Early studies done by University of Wisconsin, our friend June Lee, has shown that 3 of these EON IR mid-wave sounders, like the ones we're using for CIRAS, actually can give comparable impact to a CIRAS instrument. Now, certainly CIRAS has the long wave, it's much better, it's designed for this, for operational sounding. But I think 3 of them, this business of having, when he did it, he had them in different orbits, and I think that's why he was getting the additional benefit. The other thing we're looking at is atmospheric motion vector winds. We believe that if we have 3 of these satellites optimally spaced in time, looking at the same region of the ground, measuring water vapor profiles, that we could do effectively a 3-dimensional motion vector winds, basically wind vectors at a few different altitudes, which has never been done before. Right now, today's atmospheric motion vector winds, things like MODIS, do a total column water vapor measurement, and that you can see the total, kind of don't know where the height is very uncertain. And because of that, the wind speed is uncertain at any given height. So we believe that there's a good chance that these could support that 3D winds. And then finally, we have a great carbon monoxide absorption feature. We can use this instrument to continue to monitor carbon monoxide. I mentioned Bill Blackwell with his microwave CubeSats. He's recently been awarded a constellation of CubeSats called TROPICS, Time Resolved Observation of Precipitation Structure and Storm Intensity with a constellation of small sats. So Bill is really pioneering this idea of using constellations, and we've been talking a lot about how we can complement that with an infrared suite in the future. And I'm going to end on this animation here, which is, I think it's every 30 minutes, of a model observation of the Earth. And of course, instruments like the new ABI, the GOES-R ABI, can take video every 5 minutes of the atmosphere. What these sounders do is provide the global information. Polar does really good in the polar region, so the low Earth orbit constellation may provide another complement, not a replacement of any of these. It's just another complement to Earth observation for weather and climate. And I think, if any of us goes to the doctor, you don't want to rely on one test. You don't want to rely on one result, or you want to see multiple independent ways of observing our Earth. It's our home. So I think in that respect, the CubeSats provide a new dimension, a new opportunity to view the Earth and focus on particular aspects of the atmosphere in terms of the gases you want to look at and the orbit you want to get. So in summarizing, NASA and NOAA satellites improve weather prediction and support Earth science. They've been they're large, expensive instruments, but their value is incredibly high. Infrared sounders, AIRS, CIRAS, and EASI, have among the highest impact, next to the microwave, of all satellite instruments for improving weather forecast, and are used widely, and I mean globally. Our data is assimilated by NWP centers globally for weather forecast, and also for climate science. CubeSat technology enables low cost per satellite. How do we use that technology to complement our observations? Well, constellations. We're starting to say that might be one way to complement GEO and provide global coverage. And we also mentioned looking at different orbit times and maybe as a gap mitigation. CIRAS, the CubeSat I'm developing now with my partners at JPL and industry, is a 6U CubeSat funded by NASA ESTO. We're demonstrating key technologies that will prove these technologies in space, including the hot birds, the immersion grating, and the black silicon. And it does use extensive technologies, and I want to tell you it's a challenge. Extensive commercial technologies, and it is a challenge to use these technologies and build them into your system because they're already built, and you have to kind of work around them.
And several applications exist. I think I mentioned that already, and but I want to let you know, I think you can expect to see a lot more of these. I hope we see a lot more CubeSats for weather prediction, and I think the response that we're seeing from the university community and small businesses in using CubeSats is overwhelming. And I think this is a great opportunity for all of us to participate. Again, I want to put a plug in for the CubeSats and NanoSats Remote Sensing Conference here at SPIE, held every 2 years. We actually have only had our first one last year. There was a good turnout, and we skipped this year, and I think 2 years would be good. And then if we get enough response, we'll go to every year. And with that, I want to thank you for your time.